in this day, the temperature was not very high, and wind also, but suddenly, within 41 seconds, all becomes ignited, and they had 2 dead and 4 injured, and 6 hectares were rapidly burned. The other example of concepts not known is the junction fires, or called also eruptive fires. This picture is from the lab of Professor Viegas in Portugal. They ignited two lines, and they followed the spread of fire in the middle. So usually fire spread velocity, rate of spread is about 3 kilometers, even for extreme fire per hour, even for extreme fires. But in junction fires, firstly observed in Canberra, Australia, in 1993, was 36 kilometers. I did not believe on that, but when I saw the spread in these tables, 8 meters were completely burned in 4 seconds. In the world, with fires, fire-prone ecosystem is composed of 40% of the global land surface, and the major biomass is savanna, grassland, boreal forest, and shrublands. They are responsible of 85% of global fires. Savanna is the most fire-prone ecosystem with 65, and the land cover of savanna in the earth is about 25%. It is 50% in the south of the south part of Africa, with 15 millions of kilometers square, and the second largest cover is in Australia, with 12%, with 2 million kilometers. The future behaviors of fire spread will be influenced by climate change, less precipitations, higher temperature, drier condition, and with storm and lightning. Deforestation also is a main cause of for severity and the high intensity of fires. From NRC Global Report in 2024 concerning Europe, Middle East, and North Africa, as you can see, among the largest fires and the largest number of fires, Algeria is among the 6 first countries, with more than 40,000 hectares. It's like comparable to fires in France, but in France there were 400 fires, while in Algeria much less, only 11 fires. So Algeria in Africa, if Africa can be divided into two parts by the equator, and one is North Saharan countries, and the other one is South Saharan countries. It is separated by Sahara, which is a desert. There is practically no fires in this desert. There are different climates. North Africa is concerned with clement climate, and is composed mainly by shrubs, needles, and eucalyptus, while South Africa is composed of cover fuel is composed of savanna, shrubs, and grassland. Savanna is, as I told, 50% of the land cover of this. Savanna is in yellow color. So it appears that fires in the south part of Africa is much interesting to study because it is concerned by many prone fire fuels, but the difference is between north and the south. The north is nothing concerning the land cover, but the difference is about the roughness of the land. There is a large roughness in the lands. They are composed on many of mountains and lands difficult to access while fire. Okay. While in the south of Africa, part of Africa, they are mainly flat systems. So if you look at this satellite picture, you see that the north of the south part of Africa, composed also on forests and savanna, etc., is the most burning region of Africa. It seems that all this region is burning, but this is a picture. In this picture, the pixels are very large. So and the fires are we have small fires, but by seeing the pictures, the large pixels, there is a collapse between the pixels. That's why it appears that all this region is burning. So when analyzing the evolution of fires in sub-Saharan Africa, it's mainly decreasing. The proportion of burned areas are mainly decreasing with some oscillations due to the fuel growth and driven by savanna, grassland, croplands, and the frequency depends on climate change. So very few fires appear in Sahara due to the shrubs and the desert. There are also in the desert there are mainly palm trees, and these palm trees appear to resist to high climates, mainly beyond 50 degrees Celsius in the summer and even beyond the summer. So this may indicate that palm fuel may be resistant to fire spread if they are used in the wildland. So recent work which just have been just accepted concerned the use of their small scale investigations, tests of this kind of fuel, which when we apply a large fire, a large heat, they produce a very little heat. That's why I think they are much resistant to extreme fire if they are used in the wildland. This is the conclusion of this work, and but before it should be tested by large scale investigations. Maybe your laboratory will be one of large scale investigation in this sense. North Africa has a very small land cover compared to the southern of Africa, but they are more dangerous. Now I think it is not. I had another version. I think. Okay, not worry. In North Africa, in Algeria, mainly in the center of Algeria, Kabylie, Algeria, during the last 4 years, there were an increasing fires. The largest of them was in 2021, where 90 deaths, 90% had death, and with 33 militaries. It was impossible to reach the mountains because there were some mountains in the village, and it was very difficult. And in that year, Algeria was not equipped with aerial facilities, so that fire spread quickly. In 2023, there were also fires, but with small intensity, because Algeria was occupied in 2023 by some aerial facilities. There were, I think, 30 deaths and 10 militaries. So I come now to the application of physics to some concepts of life. Quantum physics concerns diodes and semiconductors physics, while radiation physics, ultrasound physics, magnetoresistance concerns other applications. I can speak here about Seebeck effect, which is the main concept to make thermocouples. In statistical physics, we have three ensembles, and two of them are concerned by statistical physics. Is statistics concerning how to deal with complex ensembles, and it is driven by the known Stefan-Boltzmann equation, and we have distribution distribution depending on energy, called Boltzmann distribution. For quantum systems, the Boltzmann distribution, because of the particular behavior of particles in microscopic scale, we have two kinds of statistical distributions: Bose-Einstein distribution and Fermi-Dirac distribution. I can't speak more about this concept, but it takes a long time. Bose-Einstein distribution concerns how to calculate the heating, radiation heating, and heat capacity of materials and things like this, while Fermi-Dirac distributions concerns mainly electrons, and it leads to the distinction between insulators and conductors and semiconductors. So the application of such Boltzmann distribution appears here in the study of dielectric relaxation, where it can be an Arrhenius type. The relaxation frequency depends on temperature as an Arrhenius formula. So Bose-Einstein statistics, as I told, may lead to this Boltzmann formula, by which we can understand heat flux sensors, Planck distribution, how to separate the emissivity of materials, why we have only a small emissivity or large emissivity. It depends on the wavelength. Fermi-Dirac statistics concerns the band theory of materials, and it distinguishes conductors, semiconductors, and insulators, and it can explain some semiconductors phenomena like NP junctions. In statistical physics, there is a very interesting theorem which relates the fluctuations of some quantities at equilibrium to some quantities which lead the system beyond equilibrium. Like here, energy fluctuations may be related to heat capacity. Pressure fluctuations, the number of particle fluctuations is related to isothermal compressibility. And in one of our works, electric current fluctuations have been related to magnetic susceptibility. So there is also another concept observed. Mainly, some of you have been observed this concept, but they don't care about it. Is the diffusion and relaxation process. This diffusion is a classical particle in random media. The wavelength is a random media. It can be modeled by a Brownian motion, and it is described by the known Fokker-Planck equation, which relates the derivative of the probability, time derivative of the probability with its spatial derivative. the time derivative, which is spatial derivative, and the displacement of the particles are mainly proportional to the square root of time. But in many cases, even in fire spread, we have anomalous diffusion, and in anomalous diffusion, the displacement doesn't follow this right behavior. We have a power law behavior with time. When the exponent is greater than 1, we have a super diffusion. It is faster than diffusion. And for an exponent smaller than 1, we have a subdiffusion. And it can be described by a fractional derivative. Mathematicians know fractional derivative instead of only derivatives. Yeah, I will continue. So normal relaxation. In normal relaxation, you can understand normal relaxation by looking at resistance capacitor circuits. There is a normal relaxation through the resistance of the charge while charging the capacitance or discharging this capacitance. You have an exponential behavior with time of charge. And this is related to Brownian diffusion. So relaxation is only temporal behavior of the whole systems, while diffusion is a spatiotemporal behavior of particles in the system. So in normal relaxation, it is described by this first order equation. When the function A of t is constant, it corresponds to the relaxation time, while in anomalous relaxation we have a fractional derivative, and it corresponds to mainly to this empirical formula of stretched exponential behavior, where beta greater than 1 corresponds to fast relaxation, super relaxation, and smaller than 1 corresponds to slow relaxation, anomalous, called also anomalous relaxation. An example of using this relaxation process is the material submitted to a heat flux. Dresdal in 2011 described this evolution of the mass by this first order equation, where the proportionality function depends on time with an Arrhenius law. If temperature remains constant during the process, the heating process, we have a normal relaxation. Also, when heating, dynamics of heating, it gives you the heating of the fuel. It gives you, when you neglect radiations and conductions, only convections, it corresponds to such normal relaxation of temperature. So there is an application here of anomalous relaxation. One of my students passed about 6 months in Portugal and used cylindrical baskets with a mesh shape and tried to ignite from the bottom the cylinders and examined time evolution of the mass. Time evolution corresponds to a relaxation, and he used this stretched relaxation function, and he found after a long term, at the first stage there is of the burning, there is a fast relaxation with a large exponent, and at the latter stage, after a steady state, we have a slower relaxation due to the diffusion of gases, products, and the products through the fuel. There is a slow relaxation because of the diffusion of this gases, combustible gases through the fuel. While at the first step, at the beginning, the products of combustion diffused to air, and they were helped by the flow of air. Phase transitions can be also helpful for fires, and we had two papers with this. Phase transitions, near the phase transitions, if X is a temperature and Xc is a critical temperature, any quantity can behave as this power law behavior. One example of this is the liquid gas transition, solid liquid transition, ferromagnetic, paramagnetics, insulator, conductor, and you have the quantities. For example, insulator conductor, the conductivity is zero below a certain density of conductors, and it becomes to increase like this power law behavior, starting from the threshold density. Okay. How to determine this the threshold density? It is suggested that at threshold, disorder is maximum. So when you study the fluctuations, variance of the quantity, it shows a maximum at the threshold, and you can use this power law function. So, for example, in percolation theory, percolation concerns the transition between conductor, insulator to conductor systems in many senses. The conductivity behaves as this power law behavior. It is zero below the critical concentration, and it starts to increase as a power law. And this concerns not only conductors, electrical system, fluid in porous media, virus diseases, rumors in social science and also in finance. It is applied in many fields. Percolation is a system, is a transition from conducting concerns the red particles, and insulators concern the gray particles. When starting from a concentration of red particles or red links, you have a transition from insulator to conductor. And at this transition region, the system, there is a path between the two edges of the system, composed mainly by singularly connected links. When you delete one link, the system becomes insulated. There are also some irregular networks. One of them is called small world networks, and this is in this picture. The network is one-dimensional, but if you add to the system long-range connections with some probability, you have a small world networks. This kind of networks has been applied to epidemics, to rumors, to scientific collaboration. This is this result we published in 2001 concerning epidemics, where we can separate the epidemic behavior to the endemic behavior. It has been applied in 2005 to fire spread, to simulating fire spread. We have not only an ignited cell can transfer heat not only to the nearest neighbors, but also to a long range. There are long range connections, deterministic long range connections, where we have the interaction domain by flame radiations, and also probabilistic long range connections by fibrands. And we introduce all physical and combustion physics in the behavior, temperature behavior of the cell. So another thing we can speak about is the complex structure of a burned or burning front or burned area, which is component from satellite images by lacunarities, digitations, and some cluster effects. And this has been first analyzed by Caldarelli in 2001 as a fractal dimension of fractal dimension of the system. They found the fractal dimension 1.3. So a system, when we simulate a system fire through a complex system, there is a fire pattern, and this fire pattern is analyzed by can be analyzed by a fractal dimensionality. Fire scientists, when analyzing this system, they study mainly the average rate of spread like in this case. In this case, you have this is the front, and they use the rate of spread. Sometimes they use walls, and when the fire reaches the walls, it destroys the walls, and we count the time to destroying the walls, and from this we calculate the rate of spread. So if you have a wall destroyed here in this region, in the right region, at time t1, and the next wall will be destroyed by this part at time t2, you see that the distance traveled by this point is very large compared to this one. So you have a dispersion of velocity, and velocity cannot be measured by this concept. Sometimes we use infrared camera. Infrared camera will give you, you can calculate from infrared camera the mean position of the front. So there are also fluctuations of the position of the front, which is called the width of the front, and the width of the front shows some interesting behaviors which are not up to now used by fire scientists. This is an example in our lab of the front. You have a dispersion of the flames, and you have also an irregularity of the front. So it can be, the front can be described by the effective dimension of occupation of this front. And the effective dimension of occupation can be related to the fractal dimension. I will show you some examples of fractal dimension. So just take what is called the Sierpinski map as a triangle. You divide this triangle in 4 triangles, and you remove the center one, and you do the same thing in each iteration. You will have such an image, and this image has a dimension, an effective dimension of 1.6 and not 2 instead of 2. Also, the core curve. In the core curve, you start with a line. We divide the line in three parts. We remove the central part, and you replace it by two segments, and you get this image at the end. And this image has a fractal dimension of 1.26. In general, if you have a front like this and you would like to calculate its fractal dimension, you have to divide your system in small cells of different sizes, and you vary the size. When you vary the size, the number of cells, occupied cells, will decrease. If the system is self-similar, it decreases linearly. Otherwise, it decreases non-linearly. But the fractal dimension is the slope of this function in power law, in double logarithmic scale. So we use it in 2021 this concept for a simulated landscape with different fuel occupancy, and we found the variation of the fractal dimension like this. There is the influence of the relaxation in this case. There are two technological development by using such concepts. The first one is a new estimation of the critical heat flux for ignition. So when you have a fuel exposed to a heat flux, there is a gas, flammable gas will be released, but you can have ignition or not ignition, depending on the minimum concentration of gas in the air, which is called low flammability concentration. So you can have only gases, or you can have ignition in the other case. This corresponds to two different phases without ignition and phase with ignition. By using the exposition of the combustible, there is a water evaporation and gas emission. If the gas emission reaches stoichiometry with air, you can have either an endothermic behavior with only gases, or an exothermic behavior with the flame state. So we used this concept. So you know this. There is a mass loss rate, and the mass loss rate evolves, and you can have self-ignition or piloted ignition. There are some criteria in modeling ignition, temperature criteria, energy criteria. There is a minimum energy allowing ignition, and the mass loss rate criteria when the gas reaches the low flammability limit. This corresponds to, you can find this in Quintieri book. This corresponds to self-ignition, and the other one to auto-piloted ignition with an arc or with a flame. There's integral equation can model ignition. When you reach the temperature, ignition temperature, where you have ignition, and the left part corresponds to the energy given to the system until ignition, and the other part is the rise of temperature until temperature ignition. There is a critical here energy, and here there is a critical temperature. There is also a critical mass loss rate, which is not included here, should be included. So you can see here the triangle of fire, and you have a phase transition from ignitable state and non-ignitable state. This is the process, the experimental setup by our concalorimeter made by the laboratory members. We submit a fuel to the concalorimeter, and we measure temperature and the mass of the system, the mass loss. And here there are some results, previous results in the case of they follow they show the variation of time, ignition time, as a function of the heat flux, and the inverse of ignition time, and it becomes, for large flux, it becomes linear. For thin fuels, it becomes linear, and they extrapolate this linear behavior, and the intersection will give you the critical heat flux. But near the transition, near the critical heat flux, there is no, the system becomes non-linear. So this is a wrong extrapolation. The same thing is done if you vary the moisture content, and you have you will have the time, ignition time will increase sharply after a given moisture content. These are the works of Trabo in 1984, where they used an IP radiator at 620, and they found the critical moisture content at ignition, for ignition, should be greater than 20%. When using our concept, this is the theoretical analysis of ignition time by using by varying the heat flux and varying the moisture content, you will have a power law behavior, experimental data shows a power law behavior of ignition time as for phase transitions with an exponent. And by using this power law behavior, we calculated the critical heat flux for ignition for straw, eucalyptus, and Pinus halpensis. As you see here, for Pinus halpensis, the critical heat flux for ignition is 4 kilowatt per meter square, while in literature you find 8 kilowatt per meter square. The same thing by varying the moisture content, and by varying the moisture content, we found that the critical moisture content is 100%. It means that when you have you can have ignition whatever moisture content is, provided that you apply the right heat flux. So we did some measurements of the probability of ignition for different heat flux, incident heat flux, irradiance. This is the probability of ignition. We made 50 tests, and we found that in this above 10 kilowatt per meter square for Pinus halpensis, we have always ignition. But below 9.5 kilowatt per meter square, the probability of ignition starts decreasing, and we saw this 20%, which corresponds to this region, and this region corresponds to 20%, 8.5 correspond to 20%. The 20% corresponds to one successful test from 5 tests. From 5 tests, there is 20% probability. If you have only one test from 5 tests, you have 20%, and this is why we reproduced the literature critical heat flux, but our critical heat flux is far below when the probability reaches 0, and this has dramatic consequences in fire safety, because if you put some fire breaks, fuel breaks, and between the urban zone and wineland zone, you can calculate, if you have only Venus halpensis, you can calculate 8 or 7 kilowatt per meter square in the side of urban system, and in this side you will have some surprises. Fire can spread and can ignite buildings, even if it is below their critical heat flux. While in our case, if you put 4, you calculate the width of the fuel break as to have 4 kilowatt per meter square, you will never have a spread of fire. Probabilistic behavior appears also in flammable liquids, pool fires, even if flammable liquids are not disordered. Flammable liquids are ordered, but the conditions are, there is always a kind of disorder in the condition of ignition, and you can have, thank you. And you can have the probability of ignition. But the people who made this probabilistic behavior did not think about the transition, but it occurs always. Another work we did was a new formula relating the electrical conductivity to the moisture content or the porosity of the system. So as you know, the traditional use process to measure the moisture content is to put the fuel in an oven at 105 degrees temperature during one day, and you wait after this fuel, and the difference will give you the moisture content. But when you put your system in an oven, there is not only water which is evaporated. Flammable gas will be evaporated, and you will not estimate the right moisture content. Without about measuring the moisture content by electrical system, we have an impedance analyzer which relates the impedance to the frequency, and we can impedance or conductivity to the frequency, and we can calculate the moisture content from this electrical analysis. But from the electrical analysis, you can have the relation between the conductivity and the moisture content or porosity, because the pores are filled by water. You can relate the conductivity to this porosity, and the first law in 1942 was also an empirical law, and related the conductivity as a power law with moisture content. In this work, this is not finished work. We relate the conductivity to the moisture content by using a critical moisture content. The critical moisture content is considered as the measured moisture content of the system, based on percolation theory. So this is a comparative comparison between the front simulated front and the measured by firefighters front for Lançon fires, historical fires in 2005, and we have found 15% accuracy. The last work is trying to model fire spread by using anomalous diffusion. So there are many models of fire spread, empirical models using empirical experimental formulas in these models, stochastic models like percolation, cellular automata, and also our small world model, and also semi-physical models, many semi-physical models. But up to now, we believe that computational fluid dynamics model is the right model for simulating fire behavior, because it uses computational fluid dynamics, and computational fluid dynamics use equations like diffusion equation, diffusion of water, diffusion of the fuel, and as we use the small world model, we calculate the flame radiation, the incident heat flux for neighboring fuel by considering the flame as a cylinder, Monte Carlo methods, and we simulate the behavior of fire, predicted fire. It's the red part, and real pattern. Real pattern, it is not really a real pattern, because firefighters drawn this pattern before fire arrives. It is not really the fire patterns. So one of my students, Sahila, has measured the evolution, emission of gases, the rate of emission of gases as a function of time, and he used such an empirical law of stretched exponential relaxation, and by this is the evolution of the mass, and this is the evolution of normalized mass for relaxation process. And you see here two kinds of relaxation. At the beginning, a fast relaxation, and at the end, a slow relaxation. As I explained, the fast relaxation is the emission of flammable gases, water, in the lateral positions of the basket. So it is driven by the flow, air and gas, and the other ones, the other one, when the fire reaches the surface, diffusion of gases is mainly through the bulk of the fuel, and it becomes slowly slow, very slow, and it corresponds to a slow diffusion, slow relaxation. And this slow relaxation should be, and fast relaxation should be introduced in CFD models to predict the fire spread, instead of using only normal relaxation. The relaxation of the fuels, relaxation of temperature are not normal, they are anomalous, and this anomalous kind of relaxation should be included in CFD models. There are two other other works we either we have made or we are trying to finalize, is the influence of compactness on the flammability and fire spread. We, as Rothermel found in 60 years before, other workers, there is a critical and minimum ignition time, or it corresponds to a maximum fire spread for a given compactness, which enhances the flammability, and this has been done for in a given range from 0 to 50%, and it should be extended to many other. This is only the flammability. Ignitability, we should extend this to combustibility, heat release rate, and flame height. This is in course. We show here the mass loss rate as a function of compactness, and what we concluded that in some simulation models they use only the load of the fuel, but the load of the fuel is not sufficient. We should use the load and the height of the fuel. Mainly they don't consider the height. It should be considered. Okay. Before I have still time. Okay. Before finishing, I will show you our research projects we have, as we are not only a laboratory on fire. We have some other projects in dielectrics, in percolation, in material science, in diseases, and also in fire behavior. There are few training diploma linked to our lab in license, bachelor, master, and PhD levels. We have still some collaboration with few institutions and labs, and we expect a collaboration with your lab. In the last, I think, 5 years, we have 5 PhD defended, and 2 are in course. I will show you here the facilities in our lab. We have an impedance dielectric analyzer from 3 microhertz to 20 megahertz with an impedance range from the milliohm to 100 tera ohms, which allows us investigating biological tissues, metals, composites, ceramics, liquids, and so on. And we have a cryogenic system, which allows us to do measurements from gas transition, minus 160, to 400 degrees. We are acquiring an oven, an oven to be added to the ASIS analyzer to measure the electric spectroscopy to up to 2000 degrees. We have two concalorimeters, one at the right made by us, and before acquiring a concalorimeter from FTT, fire testing technology. We have a radiant panel allowing measuring the index of spread, bomb calorimeter, and oxygen index. We have also parts of measurements. We have borrowed parts of measurements to do experiments on fire spread. So these are the main research topics. This is the room. It's 100 meters squares room. These are the members. These are the students and technicians and researchers. Thank you for
It is a wonderful lecture by Professor. Now it's time for questions. If there you have any question, please.
Professor, thank you for your report. You have applied small world networks to history facts such as Corsica and Savannah, and I have a question about how you consider the balance between site resolution and the quality of predictive heat transfer model scale.
Thank you very much. It's a good question, and it's the question which is also asked by us before doing simulations. When doing the simulation, the first question we asked, which, because the simulation is on a network, square network, triangular network, and what is the side of the network? The side of the network is considered as the side, the diameter of the trees. But if you have a surface fire, the network becomes continuous, and it's a problem to simulate this network. If you have trees, it corresponds to the side of the trees. If you have a surface fire, you should include a given diameter of the system, which is not always the right diameter, because by by studying the flames, the diameter of the system is the diameter of the flames, not this of the system, not of the trees, the diameter of the flames. And we are still working on this. Regarding the heat transfer, we consider convection and conduction heat transfer. Convection depends on wind spread, and radiation corresponds to the influence of the flames. Okay. the influence of the flames on the neighboring strat of the fuels. We have seen this. This one. We consider the flame as a cylindrical flame, and we use radiation emission from the surface of the flames. We neglect the bulk emissions. We consider the emission of the flames from the surface, and we calculate the total emission, total influence of these radiations on the neighboring, on a fuel at a distance, a given distance from the flame. And we do the sum of this heat intensities, and use this heat intensity as the incident heat intensity to ignite the fuel. Is it this what you?
Yes.
This is not. This is still time consuming, because Monte Carlo, it is calculated by Monte Carlo simulations, and Monte Carlo simulations requires more that the network of the cylinder, you have more mesh emission. The number of emitted flames quanta should be much higher. But if you put a much higher number of quanta, you will have a time consuming for one cell. You will need about 1 week. It is not working. What we do in this case for simulating with fires, we use a smaller number of emitted quanta, which is not accurate. So we have no a formula, because the cylinder is a known geometry, and we can calculate, integrate the quanta, and we can calculate the radiation from a cylinder to a given fuel. We introduce it. We have introduced this recently to our model, but for the Savannah, the model simulation of Savannah and Alonso, we used only 1,000 quanta per meter square, which is very low and induces many fluctuations.
Thank you for your presentation. I have a question for the industrial company.
Yes.
In your research, do you know that the scrap with the industrial
20%, critical moisture content.
Yes. However, in farm fire, the valve is sustained even if so this difference yes, the critical moisture content difference.
It's very different. 20% is not our result. 20% is the result of trouble. in 1984, I think. This one. This is trouble experiments. These are trouble experiments with a radiator at 600 degrees. But in the case of crown fires, you have an incident, an irradiance from intense fires, from radiation fires, flames, brilliant flames of more than 100 kilowatts per meter square. So they will always ignite fuels, even with much higher moisture content than 20%. So you can, in crown fires, you have much higher moisture content, but you have also much higher incident heat flux irradiance. So that's why what we have shown here is that always we have a critical moisture content. Theoretically, we found the critical moisture content of 100%. So if you have 90% of 90% moisture content, you will find there exists a heat flux, a very large heat flux, which will ignite this fuel because it is sufficiently high to evaporate all wet water and to ignite the remaining fuel, dry fuel. 20% is not our result.
Thank you, Professor, for your presentation. I have maybe three questions. First question about because, like as we know, fire is very serious in African basin. Like you showed some picture satellite. My question is as there is government from the country, whether they provide enough financial support for scientific research by the fire side, and especially for the international cooperation between the country and the European and other countries like China, and whether the government country have enough support financial cooperation for fire side. Thank you. This is the first question. I will have another question.
If I understand your question, if our team have a support, they can go to China to do research. It is what
no, my question like Africa has many firefighters.
Yes.
Yeah. So if your country, your government, they have enough support.
Yes.
In finance.
Yes. Yes.
Support staff between different countries, between your country and China and
yes.
other countries. Whether we can provide financial support for international research is your team in your country.
Yes. I think if there is a support, we can start research and international research between our country and your country. It is always possible. The only problem is the large traveling time, but we can contribute to your research, and you can contribute to our research. You have many facilities to contribute to our research. The problem is with the crown fires, when studying crown fires and large-scale experiments. For example, we found that palm trees, the leaves of the palm trees are against fire spread. But these results should be confirmed by large-scale experiments. We don't have large-scale experiments, but you have large-scale experiments. But the problem is how to bring with us all the palm tree to do experiments here. This is a problem. If you have palm trees, it's not a problem. If you use your facilities and large-scale facilities, and we use our fuels, it is not a problem. We feel with leaves and pines and things like this, it is not a problem. But when using large scales, you should bring with us a large tree, which is impossible, except if such trees exist in China. And we should compare the ignition and flammability properties of your fuel in our and our fuel to see that they have the same or similar properties to do the same thing with large scale fuel.
Okay, thank you. So it's easy for you or for your team to get a grant or get some foundation for your company for your study for fire. Later it's easy for your team to get funding from government to support your research on fire.
It is difficult.
It's difficult.
We have some funds, but the funds are very, very, very small, very limited, and to support the works we expect to do, it is not easy.
It's difficult. Yes. It's very competitive.
Very,
very competitive. Yeah, because in recent years, the climate change, they introduced the extreme fire condition. Also in China, maybe they have more opportunity.
Mm-hmm.
Also for the international cooperation. So they have more opportunity. And another question about for my research, I focus on the satellite study, the remote sensing.
Satellite, yes.
Satellite study, remote sensing study for the wildfire. So if you have some, because I see you have a slide. You have a slide to introduce the satellite, use the satellite MODIS, right?
MODIS, yes.
Yeah.
It is just to show that fire pattern is irregular, and irregular is not regular. Yes, and yes, this picture.
Yes, yes,
this picture. And that in this picture, how do you are able to measure the rate of spread, the fire velocity?
Fire
velocity, the rate of spread of fire. It is not possible.
I can use the satellite MODIS image to.
You can use the satellite MODIS image, but in the satellite image you have not every a few minutes a satellite image. You have every 2 hours, 3 hours, 4 hours, and the system has changed completely after 5 hours. So you cannot measure the velocity of fire, and I don't know what is the meaning of velocity in this case. So if you want to measure the dynamics of fire in this case, you should not, I think, in my point of view, you should not use the rate of spread. The burned area is okay. You can use the burned area, the evolution of burned area. But here also you have some lacunarities, and these lacunarities, when the lacunarities are very large, you can see them. But if you have lacunarities of a few pixels of the image is 100 meters. The best image has a pixels of 30 meters by 30 meters.
Yes, exactly.
Yes.
Because it's an image.
Yes. But if you use 30 meters, you can have lacunarities of a few meters square, of 10 meters square. So for this pixel image, all the pixel is occupied by fire, but it is not all occupied by fire. It's like in the case of African fire. In African fires, at the beginning I showed you here. It seems that all the Central Africa is burning.
Yes.
It is not the case.
Yes.
It is not the case. You have only small fires, but the resolution of the image is very low.
Yes.
You have 500 meters by 500 meters, so that, but the fire size is 10, 20 meters, 40 meters, so that instead of 100 meter by 100 meter, you have only 40 meters square, and the image will show you that all the 100 meter square is burning. It is not the case.
Yes, you're right. That's a limitation.
This is the limitation. You should add some aerial images from planes, from drones, to improve the resolution.
Yeah.
And to see this.
So are you interested in the study to use the satellite resources and provide it back? Because I'm interested in that topic.
Yes.
Yeah. If you are interested, you can have some research together.
But indeed, yes, it's also our interest. But we found another way to analyze these images by varying the resolution of the image of the pixels, by trying to use from low resolution to high resolution, the evolution, the variation of the resolution from low resolution to high resolution, you can get the fractal dimension. And this fractal dimension measures with the best accuracy the occupancy of your of fire, instead of only of seeing the images, because seeing the images with the low resolution will not give you any. This means that all this area is burning, yes, but it is not maybe when you see the fractal dimension, you will find that maybe 10% of this area is burning and not all the area.
Okay. Thank you, Professor.
Thank you, Professor, for your interesting points in the typing experience. My question is, you use base efficiency theory on ignition of moisture weight on weight materials. You figure on the ignition delay time on the relationship on the ignition delay time on the moisture content by a parallel expression.
I don't.
Power law.
Power law, yes.
My question is, what is the meaning of the power relationship with the power?
Power relation to
relationship. For example, P equal weight parallel alpha. Or what is alpha?
Yes. I have it in this. It's for moisture content or yes.
Your parallel relationship third W.
W is the moisture content.
Yeah, minus 3.6. What's the meaning of the
Yes.
what's the meaning of
the formula here, you see, as you see, you have a double logarithmic scale. So the line in a double logarithmic scale, if you draw here the present ignition time as delta W, which is the critical moisture content. Yes, you have the power law appears in the slope. Slope corresponds to the power. And the slope
taking on the scale of the moisture content?
What we do, we change the critical moisture content as you have the linear behavior, this line. For another critical moisture content, you don't have this linear. You have an earlier linear behavior. By changing the critical moisture content, the value of the critical moisture content, you will reach this linear behavior. And this will give you the critical moisture content, which allows you to have this linear, this power law behavior. And this corresponds to the transition. In our point of view, in the point of view of phase transition, this corresponds to it. Then we found here the exponent is not analyzed. The exponent corresponds to different ignition process. You need ASIC ignition process, not ASIC ignition process. But the measurement of the the critical moisture content, which is 100%, is from adjusting data as you have the critical moisture content.
Hello, Professor. Thank you for your presentation. I've got a small question for the past year. In the past day, you mentioned that ignition in the neighboring sites use the constant heat flux. My small question is that how is the constant heat flux calculated? Determined? Is the constant heat flux divided from small-scale experiments or from empirical data in real files?
From small-scale experiments. Yeah. And it is not right. A constant incident, that's another problem with the simulations. Using a constant incident flux, it is not realistic, because when you have a spread, you have an ignition of the fuel, and for the ignition, while you have the ignition of the fuel, the heat release rate starts increasing to a maximum, then decreasing slowly up to a minimum. And that's one of the problems the issues we try to solve with our model, our simulation model, because we should introduce this time evolution of the incident heat flux, which is not introduced in the model, which is only constant. So, but this will have other problems, because from which heat flux, heat release rate we should start, and which heat release rate we should introduce, because there is a critical heat release rate, critical heat incident heat, which allows ignition. So we should look at the heat, not start from zero, start from the critical heat release rate, and integrate our evolution to have a mean constant heat release rate. But the best solution is to introduce the time variation of the heat release rate. It's a good question.
Yes, thank you.
Thank you.
Thank you for sharing. And I have really which on the combustion in the 2007, and you use this model network to model in the fire spread and the sporting fires. And the question is, as you mentioned in this, the sporting process is there is a vibrant generated from one boarding set to another boarding set, and the secondary fire, which is ignited by the sporting fire, the fire spread vibrant, and this new boarding set can also generate another vibrant to ignite another boarding set, onboard set. So the problem is, in the real life, I can imagine such a scenario. Typically the vibrant was generated from the crown fibers, the top of the tree.
So not only
that on the ground.
Not only from the top, from the trunk, the branch.
Yes.
The height of it can be emitted by this. Not only from from the crown, because the crown is composed of fine fuels, and the fine fuels will burn, will not mainly not emit firebrands of few millimeters on or up to 1 centimeter diameter. Which part of the trees will emit such firebrands, which will travel through the panache up to 1 kilometer to 2 kilometers. It's the branch, the part of the tree, not the crown, below the crown. Yes, you have transition from surface fires to crown fires, and you have a fire is growing through this part up until the crown fires. And while the fire is growing, this part is heated and can emit some particles. Small particles will travel, which will travel through the panache. Not the emitted particles in the crown will not travel large, and will not be effective for creating a secondary fire. So from this part of the tree, you will have some particles sufficiently ignited in flaming, which will drop in far from the tree, and if it finds vegetations able to ignite, they will ignite, and they will not be sufficient to create another. The probability to create another firebrand is very, very small. It will create it because there will be also surface fires, ground fires. Then the transition from ground fires to the crown fires in another tree, you will have some time to emit another firebrand. It is not only from the crown.
Yeah, my question is, the firebrand maybe generated from the crown fires or from the.
It can be.
It is generated by the brush.
Yes.
The question is, because in your model, this process are very simplified. So, for example, the firebrand generated from one pollen set and then transport to another pollen set, and then you ignite a new fire, and this new pollen set generate another firebrand, which means I think there should be some process which is like the surface fire transformed to the brush fire.
And time also.
Yes, yes, they need some time, but in model they didn't mention that. So I was wondering how this time the firebrand landed from a pretty higher, like a tree or the brush, and landed to the ground. How ground fire?
From the panache, through the panache.
Yeah.
It will travel through the panache, not near the firebrands emitted near near the tree will have no consequence on the fire spread. The firebrands emitted far from the tree have more consequence. They create a new spotting fire, new secondary fire, which will spread, and then when spread on a surface mainly, and when it finds a tree, it will grow through the tree and emit another secondary fire, another firebrands. This will take more time. Growing through through the tree will take not a few seconds, maybe few hours. So time is important. In this work, we did not use the time. We used the probability of creating a secondary fire, and this secondary fire will grow, and you will have also another probability to emit another fire. But when you see it is shown in the paper. When you see this secondary, you have only one or two secondary fires. You have not many secondary fires. This isn't introduced in the probability. We do not simulate the secondary. We can't simulate them, but we included all these processes in a probabilistic behavior.
The previous study, it was the target was get the homogeneous experiment, and then you use this parameter to simulate the heterogeneous media. And the question is, the grade was considered 300 times 300, and the space between two coordinates is like 0.33 meter. So my question is, when you the influence zone of the brain states, maybe like 3 or 4 space, like 1 meter. But as you mentioned, the spawn fire transport far away from the state. So how to make sure this pyramid can be used in different situations?
This is a problem with scale effect, because in small scale we use a constant compactness given conditions of airflow and fuel flow, which will be different at larger scale, because the flow is different and the compactness will be varying. And in this case, not only the firebrands is a part, but also considering all this range of compactness instead of one compactness is also a problem. This makes the large scale not correlated to small scale. There are some works of Corsican peoples with large scale. They did not find the correlation between large scale and small scale. And this is because the fuel at large scale is different from the fuel at small scale. At least the fuel at small scale is a part of the fuel at large scale. This is the difference. Even if for the fuel at small scale, if you use a compactness of 10%, it means porosity of 90%. You don't have in the small scale the same porosity. You have a distribution of porosity that makes the ignition fluctuating and spread also fluctuating. This is one of the aims of this talk, that fluctuations have some origins, and they should see the origins of these fluctuations. This problem of large scale and small scale scaling effect is very important, but when doing scaling effect, I think, in my point of view, we should use small scale, moderate scale, and large scale and field scale, some different scaling effect to see how it behaves. No, people use the large concalorimeter and small scale concalorimeter. Between them, there is an intermediate scale, and this doesn't allow you to extrapolate to field scale. That's the problem.
Thank you.
was accident about the question. I'm curious about the reason of the fire happening in Africa, and whether the fire is caused by nature, or caused by human, or even caused by war. So, and the percentage of the fires. That's it.
You mean how to distinguish the origin of fire?
No, I'm curious about the reason of the fire.
The reason, yes.
Reason of the fire.
Is it from humans or is it natural?
Yeah.
But they are always made from humans, because humans leave some bottles and things to increase to make easier ignition, and they can be used by them, especially they want to do it, or by some negligence they don't care about, and there is an ignition. I don't think that the human origin is a problem of the spreading. You have a point ignition, and it will spread. This point ignition, whatever it is from humans or other things, it will spread. If the cause of ignition is not human, sun can ignite Wyland. So Wyland is not ignited by sun. So there are small things left by humans which cause ignition of fire, mainly. Or humans may ignite by themselves fire. But this the origin is a speculation. I think it's a speculation. The origin is mainly 1 or 2 point ignition, which makes the fire propagate. There are prescribed fires, which are made especially by humans to study the propagation of fire, and in some safe conditions, and this is also studied. So this is not the spread depends not on the cause, they depend on the condition of spread. Meteorological conditions, sometimes when trying to do prescribed fires, we cannot do them because weather do not allow. So when the condition is fulfilled, there is a fire spread. And fire spread, ignition, the initial ignition is one thing, and how fire spreads is another thing.
Thank you. Thanks.
Okay, so we can finish. Thanks for all the questions. And let's thank Professor
Zekri.
Thank you, everyone.
Thank you for attending.